Welcome to today's lesson, where we'll discuss what are and how to write single replacement reactions. A single replacement reaction, sometimes called a single displacement reaction, is a reaction in which one element is substituted for another element in the compound. The general pattern of a single replacement reaction can be written as AB plus C, reaction arrow, CB plus A. We can see that A is replaced by C in compound AB to make a new compound CB and element A. There are two types of single replacement reactions: cation replacement and anion replacement. In cation replacement, pure elements always substitute the first element in the compound. Why is that? Well, if we think logically, magnesium is a metal and in the periodic table has a positive oxidation state of +2. So it must substitute an element that also is positive. In this case, it is silver. Do not forget that a pure magnesium oxidation state is 0, but in the compound it becomes +2. In our second example, no reaction occurs. But why is that? In the single replacement reactions, we must always look at the metal reactivity series. Pure metal must be more reactive than metal in the compound. In the metal reactivity series, we can see that the most active metals are at the top and the least reactive at the bottom. In our first example, magnesium is more reactive than silver, and that is why a reaction occurs. But in the second example, copper is less active than zinc, so no reaction is observed. In the anion replacement, we have an opposite story. In this case, our pure element is always a nonmetal. In a single replacement reactions, nonmetals always obtain a negative oxidation state, so they substitute the second element in the compound. In this example, pure bromine replaces iodine to form a new compound. In this reaction type, only 7A group nonmetals, which are usually called halogens, are used. In our next example, no reaction occurs, and once again, it is related to the activity. If we look at our nonmetal reactivity series, we will see that the most active halogen is fluorine, and least reactive is iodine. In the first example, bromine is more reactive than iodine. But in the second example, iodine is less reactive than chlorine and the reaction doesn't occur. That's it for the theory. Now let's do some practice. Our first reaction is a reaction between copper to sulfate and pure iron. Before proceeding with the reaction, we want to look at our metal reactivity series to find out if the reaction occurs. As we can see, iron is more reactive than copper, so a reaction occurs. Iron replaces copper and forms the compound with the sulfate anion. Also, pure copper forms. Now iron oxidation state is +2 and the sulfate is -2. Equal charges cancel each other out, so we get FeSO4. Lastly, we don't need to balance this chemical reaction because we have an equal amount of the same atoms on both sides of the reaction. In our next reaction, zinc chloride reacts with nickel. Once again, let's look at the metal series. This time, nickel is less active than zinc, so no reaction occurs. What about the reaction where calcium bromide reacts with silver? Well, let's look at the metal series to find out. Calcium is way more reactive than silver, so in this time, no reaction is observed. This time, we have a reaction between nickel-free phosphate and iron. In our metal series, iron is more active than nickel, so we can proceed with the reaction. Iron forms a compound with phosphate. Iron is +2 and phosphate is -3. So the formula is Fe3PO4 times 2. Also, we add pure nickel to complete the reaction. To balance it, we add the coefficient 3 in front of pure iron and 3 in front of pure nickel. In the last example, sulfuric acid reacts with sodium. In the metal reactivity series, we can find hydrogen right over here. And like always, we look which particle is more reactive. In this case, it's sodium, so we can write a full reaction. Sodium replaces hydrogen and forms NaSO4, where sodium is +1 and sulfate -2. Our formula is Na2SO4, and our next product is pure H2 gas. Do not forget that pure hydrogen is a diatomic molecule, so we write it with index 2. Now let's write some anion replacement reactions, and we will start with the reaction between potassium bromide and fluorine. If we look at a series where nonmetals are involved, we will see that fluorine is more active than bromine, so a reaction occurs. Fluorine replaces bromine and we get Kf and pure bromine. The potassium oxidation state is +1, fluoride is -1, so the formula is Kf. Also, do not forget that all pure halogens are diatomic molecules, so we write them with index 2. To balance the reaction, we write the coefficient 2 in front of Kbr and Kf. Next, we have an iron-free chloride reaction with bromine. In our series, chlorine is more active than bromine, so no reaction occurs. And lastly, we have the reaction between manganese iodide and pure fluorine. Fluorine is way more reactive than iodine, so we can proceed with writing the reaction. We get MgF, where magnesium is +2 and fluorine is -1, so our formula is MgF2. Also, pure iodine is produced in this reaction. We don't need to balance this reaction because we have an equal amount of the same atoms on both sides of the reaction. And that's it for today's lesson. Thank you for watching. Please like and subscribe for more chemistry content. And like always, I will leave few exercises with answers that you can do on your own, and see you in the next lesson.